Dear learners, today I'll be talking about metamorphic processes. This is a part of the course Petrology. Course code is BGYCT135. I am Professor Bhaskar from School of Sciences, Indira Gandhi National Open University. The outline of my talk will be as follows. First, I will explain the cause of metamorphic processes. I will also tell you how the PNT conditions in the crust and mantle cause metamorphism. A brief introduction will be given to you about the heat flow and the geotherms and what are the applications. Then I will explain the various chemical reactions which lead to metamorphic processes. Ultimately, these processes will give rise to products of metamorphism. I will also conclude by telling what are index minerals and what is the importance of the metamorphic rocks. Now, dear learners, what is the cause of the metamorphic process? Obviously, there must be something which is occurring within the mantle and the crust which can lead to metamorphic process. There are essentially three factors to consider. One is if there is a mechanical disequilibrium. Second point can be if there is a transient chemical change. And the third one can be when there is a thermal alteration. Please remember that metamorphic rock is an isochemical change. It is a solid state change where there is no liquid formation involved. Now let us see how the dynamic processes that occur within the earth are responsible for the metamorphic processes. Because dynamic processes are occurring and because of these changed conditions are there is metamorphism because of the disequilibrium caused. Now, these metamorphic rocks are formed because the rock tries to achieve the stable state condition. And if it is older assemblages can be fully or partially replaced. If there is complete reaction, then this obliterates the earlier mineral texture. But if it is incomplete reaction, then the original texture or minerals, is partially wiped out. So these are due to the dynamic process occurring within the earth. There are metamorphic processes which can be considered essentially as chemical reaction between two or more minerals or chemical reactions between minerals and gases and between fluids and liquid. Friends, what is important here is H2O plays a prime role. And this can be also viewed as a thermodynamic process where there is an exchange and transportation of heat and substances between two domains acting as two different systems. Here it is important to consider time because it may not be a continuous process, hence metamorphism can occur in different episodes. Let us now look into the PNT conditions in the crust and mantle. When any rock is subjected to stress, it will result in transfer of some property to compensate for the effect of the applied force. So this pressure, the stress will cause metamorphism. And if there is a temperature change, a temperature gradient is there, then heat transfer will take place between high and low temperature rock units. This heat transfer will stop once equilibrium is reached. Obviously, the direction of heat flow will be from high heat source to a low heat sink such that the heat vector is perpendicular to the temperature isotherms. Now, heat flow at the surface is a combined effect of three factors. From where does the heat flow occur? One is conductive heat transferred from the interior of the earth. Second is, you are aware, there are long-lived radioactive elements which decay and that causes the heat transfer. And the transfer occurs through the process of convection the mantle convection. So this is the relationship how the heat flow and geotherms are related. Now, what is net heat flow when it is zero? When inflow equals to outflow. This is where it is a steady state geotherm. It can exceed or it can be less. If it exceeds the outflow, then excess crustal heat would fuel endothermic reactions or raise rock temperature. And if heat loss occurs, if the outflow exceeds the inflow into the crust, in such cases, because of heat loss, rocks can cool. And if the rocks cool, there can also be exothermic reactions which can generate additional heat to counteract this cooling. Now, you all know high heat, high pressure, hot, mineral rich fluids, or a combination of these factors transform pre-existing rock into metamorphic rock. This process involves the transformation and adaptation of mineral and rock deposits to achieve equilibrium under altered environmental conditions. Now, what are the different chemical reactions that lead to metamorphism? There are various kinds of reactions. We will discuss one by one. What is solid state reactions? What is exchange reactions? What are polymorphic reactions? What are solvous reactions? Reactions involving volatiles, dehydration reactions, decarbonation reactions, mixed volatile reactions, and oxidation reduction reactions. Now let us see what is solid state reaction. Reactions that involve the solid phase of the reactants is called as solid state reactants. Here, all these solid reactions are potential candidates in qualifying pressure and temperature. That means these solid reactions can be used as geobarometers or geothermometers. That means we can estimate the temperature and pressure conditions. Solid reactions can take place by the following process. For example, there can be diffusion of ions from one mineral to another. This is transfer diffusion. Second, there can be reorganization of the crystal structure. The third possibility is removal of water from a hydrous mineral, and the addition or subtraction of ions through an active fluid can be another process. Now, these solid reactions, when you talk about them, hydrous minerals contain OH ions, as you know, and anhydrous minerals are water-free. What happens? Dehydration reactions, when they occur, they expel water from the hydrous mineral to make them more stable anhydrous minerals at greater temperature and pressure. That is why the minerals which are formed at greater temperature and pressure are devoid of the hydrous minerals. Now, geobarometers and geothermometers, they are different concepts, and they are based on solid reactions. Geobarometers are minerals or a group of minerals whose existence, coexistence, or element distribution is stable between known pressure limits at given temperature. That means if you know the distribution of the group of minerals, then you can find out the pressure, because it is at a given temperature, it is stable for the known pressure limits. Now, geothermometers are natural mineral systems which are used to estimate the temperature that produce an equilibrated mineral assemblage in a metamorphic rock through element partitioning between minerals. So, geothermometry is used to estimate the temperature, and geobarometers are used to estimate the pressure, and these are based on the mineral systems which exist. Now, these equilibrium conditions are independent of fluid phase composition for such reactions. Now, what are the examples of solid-solid reaction? There are two types: net transfer reaction. Transfer of components may take place from reactant phase to product phase, which may involve both anhydrous and volatile phase components. These are called coupled reactions. Essentially, there are two types: terminal reactions, a phase completely disappearing after a certain pressure temperature limit. Example, you can take jadeite plus quartz gives albite, which is a anhydrous phase. Non-terminal reactions, in this type of net transfer reaction, the mineral assemblage either appear or disappear. Example is diopside plus Al2SiO5 will give rise to grossular plus pyrope. See, these are examples of solid-solid reaction type. Now, the next reaction type is exchange reaction. The name itself tells you that when exchange of component takes place only between certain anhydrous or volatile conserving mineral phases, only then such a reaction is called as an exchange solid-solid metamorphic reaction. Now, what happens here? Phosphorite, if you see, plus ferrocylite will give phthalite plus enstatite. Now, this is an anhydrous phase, and here FeMg exchange takes place between olivine and orthopyroxene. The other example is pyrope plus annite will give almandine plus phlogopite. Again, this is a volatile conserving phase. The next type of reaction which occurs is the polymorphic reactions. Now, polymorphic is again solid-solid reactions, and transition in phase takes place, but the mineral chemistry remains the same. But the mineralogical phase transits to another polymorph. The chemical composition is same, but the structure, mineralogical phase transformation occurs. For example, calcite to aragonite or graphite to diamond. Here what happens? It involves the transformation of mineral into a second mineral having the same chemistry but with a different crystal structure. For example, calcite and aragonite have the same chemistry but different mineral structure. Graphite and diamond have the same mineral chemistry but different crystal structure. Now, the classic example is aluminosilicates. You can have polymorphs, sillimanite, kyanite and andalusite. They have the same chemistry but different crystal structure. Polymorphic minerals have different characteristics even though their formula is same because the chemical composition is the same. Now, there is another kind of reaction which is known as solvous reaction. This reaction occurs in a limited solid solution, and this is below the critical temperature defining the solvous, or in phases exhibiting complete solid solution at high temperatures. So, this is called as solvous reaction. In this type of solvous reaction, exolution of a new phase along some slip plane takes place from the prior phase. These reactions are very useful to understand geospeedometry, that is assessing the rate of metamorphism, and geothermometry. For example, calcite, dolomite, plagioclase, potash feldspar. The next one reaction is the reactions involving volatiles. Appearance or disappearance of phases makes such reactions considerably of net transfer type. The next type of reactions are dehydration reactions. The word itself tells you that these involve water in metamorphic reaction. This is the common scenario which makes these metamorphic reactions most common. These reactions show higher temperature products which usually lack H2O. Now, when there is prograde metamorphism, that means the grade is increasing, that ensures the removal of H2O from the hydrated phases. That is why it is called dehydration reaction. The removal of hydrates is facilitated by increasing temperature during the prograde metamorphism. You can see the following reaction: muscovite plus quartz, when they combine, they give sillimanite plus potash feldspar and water is released. That is why this is called a dehydration reaction. Now, decarbonation reaction, again, the name itself tells you that carbon dioxide is removed. Metamorphism of calcareous and other CO2 bearing rocks releases carbon dioxide. That is why it is called as decarbonation, that CO2 is removed. And which are the relations, which are the minerals involved? Carbonate minerals. For example, dolomite, calcite can release CO2 when they decompose. Now, it is quite likely that it may not be pure CO2. It usually exists with water or other volatiles. To give an example of decarbonation reaction, it is CaCO3 plus SiO2, CaSiO3 plus CO2. So, the carbon dioxide is released. That is why this is called as decarbonation reaction. Now, there is another kind of reaction which is responsible for the metamorphic processes, which is known as mixed volatile reaction. Again, the name tells you it is volatile and mixed. There are two fluid phases, CO2 and H2O are involved, and the reaction takes place in two ways. And the two ways are such that both the fluid phases are on one side. That is, it can either be on the reactant side or product side, or fluid phases are in the opposite sides of the same reaction. Now, I will give you two examples. Margarite plus 2 quartz plus calcite is 2 anorthite plus CO2 plus H2O. If you see, both the fluid phases, CO2 and H2O, are on the same side of the reaction. This is a mixed volatile reaction. And the other one is 5 dolomite plus 8 quartz plus H2O is tremolite plus calcite, 3 calcite plus 7 CO2. Here, if you see, the fluid phases, that is CO2 and H2O, are in the opposite side. They are called mixed volatile because there are two volatiles, and these can occur either on the reactant side or product side, both, or it can, equally divide themselves in both sides of the same reaction. Now, the next one is the oxidation reduction reactions. Now, oxidation reduction reaction means there is a change in the oxidation state. One or more elements take place during this type of metamorphic reaction. Unlike other metamorphic reactions, redox reactions may not involve volatile components in the reaction. Redox reactions may be formulated in ionic form also. For example, 2Fe3O4 plus half O2 will give 3Fe2O3. So, a change in oxidation state has taken place in this reaction. Now, there are different products of metamorphism, and these products of metamorphism are metamorphic minerals and metamorphic rocks. Now, metamorphic rocks can yield attractive minerals, and for example, garnet, corundum, varieties of which include sapphire and ruby, kyanite, all these things are there. And metamorphic rocks, minerals form in a place within a solid rock because of changes in temperature and pressure. Now, the mineral assemblages that occur in a metamorphic rock is essentially controlled by four factors. One, obviously, what is the bulk composition of the original rock? Second, what are the pressure conditions during metamorphism? Third, temperature conditions during metamorphism. And fourth is the composition of the fluid phase during metamorphism. Now, a rock under high pressure and temperature develops a mineral assemblage reflecting stable chemical equilibrium. Now, when the conditions are sustained, they lead to equilibrium conditions. Since metamorphism can span long geological time scale, most metamorphic rock reflect an equilibrium mineral assemblage. Now, metamorphic rocks are dominated by minerals such as feldspar, quartz, muscovite, biotite, amphibole, calcite, and dolomite. And a few minerals are exclusively found in metamorphic rock, and some of the important metamorphic minerals are actinolite, almandine, that is a variety of garnet, andalusite, anthophyllite, aragonite, brucite, chlorite, chloritoid, cordierite, corundum, diopside, enstatite, epidote, phyllite, fosterite, glaucophene, grossular, which is a garnet, hematite, heulandite, hypersthene, ilmenite, jadeite, kyanite, lawsonite, magnetite, periclase, prehenite, pumpelite, serpentine, sillimanite, sphene, staurolite, talc, tremolite, and wollastonite. Now, there are certain concepts which are called index minerals, and index minerals show the grade of metamorphism. That means how much the original rock has metamorphosed. And because the stability range of each mineral remains small, these minerals serve as indicators of metamorphic conditions. And indicator minerals serve as effective indicators for metamorphic conditions. If you see the diagram here, different minerals are formed at different temperatures. Chlorite, low temperature; muscovite, biotite, increasing temperature; garnet, andalusite, and sillimanite. So you can see the range of temperature, how the minerals change, and they give an indication of the conditions of metamorphism. Now, what is the importance of the metamorphic rock? Obviously, they provide insights into the physical and chemical changes that take place deep inside the earth. And these index minerals allow geologists to understand and assess the temperature and pressure conditions that the parent rock encountered. Also, metamorphic rocks have economic value, and the knowledge of metamorphic process and rocks is very significant. Now, metamorphic rocks, if you see, like slate and marble, are used in building materials. Talc is used in cosmetics, powders, paints, and lubricants. Garnet is gemstones and abrasives. Graphite is insulator, refractory, and lubricant. Asbestos is used, for insulation and fireproofing. Metamorphic rocks are oldest rock present on the earth, and these are exposed in core areas which are known as continental shields and form much of the roots of the mountain ranges. Just to bring a summary, metamorphism is a process, as you know, which brings about changes in mineralogical, structural, or chemical constituents in a rock, and dominantly solid. There is no liquid phase. Metamorphism is regarded as a thermal phenomenon in which heat is an important source of energy, causing, mineralogical and textural reconstruction. Metamorphic rock, is formed by recrystallization of pre-existing rock. It can be igneous, sedimentary, or even metamorphic rock by mineralogical, chemical, and structural changes in response to temperature, pressure, and chemically active fluids at the depths of the Earth's crust. This is a part of the rock cycle, and it is related to plate tectonics. Again, if you see changes in temperature, pressure, shearing stress, chemically active fluids or gases cause metamorphism in rock. These fluids or gases may leave the system but can be trapped as fluid inclusions in metamorphic minerals formed at considerable depth in the Earth's crust. So we can understand by studying the fluid inclusion, the nature of fluids which are trapped. Now, the source comes obviously from deep inside the earth, and as I said to you, it is the decay of radioactive elements. Also, the frictional heat generated along the faults or shear zones, or the latent heat of crystallization from igneous intrusions and magma. The range of metamorphism which occurs at temperatures and pressure is temperatures higher than 150 degrees centigrade and pressures greater than 300 megapascals. So this is how it occurs. And what is protolith? It is the original rock prior to metamorphism. There are different type of protoliths. They can be quartzofelspathic, pelitic, calcareous, basic, ultrabasic, and ferruginous. Now, the chemical reactions responsible for alteration or modification in the mineral composition of the rocks are of different reactions. They can be solid-solid reactions, exchange reactions, polymorphic reactions, Solvus reactions, reactions involving volatiles, dehydration reactions, decarbonation reactions, mixed volatile reactions, and oxidation reduction reactions. Now, metamorphic rocks form within the solid rock due to changes in temperature and pressure, and the development of mineral assemblages in the metamorphic rock depends on four factors. What is the bulk composition of the original rock? What are the pressure conditions during the metamorphism? What are the temperature conditions during metamorphism? And what is the composition of the fluid phase during metamorphism? Metamorphism, is a part of the rock cycle, and index minerals are the minerals in the metamorphic rocks which can indicate the grade of metamorphism, how extensively the original rock has metamorphosed. Depending on that, they will indicate the minerals, what is the temperature and pressure range they have undergone. The metamorphic rocks and minerals have economic value, and metamorphic rock obviously provide insights into the physical and chemical changes that take place deep within the earth. So learners, I am sure you must have understood the different metamorphic processes which take place, the different kind of chemical reactions that take place, the products that are produced, and what are the index minerals which give you the indicators of the temperature and pressure in metamorphic processes, and what are the reasons why we should study metamorphic rock. Thank you very much for a patient hearing.